Wi-Fi goes to the end.
You're using the casino or the
Casino.
It's better.
It's very slow.
Well,
Good morning. I think we can start to the third edition of the International Workshop on Spectral Cell Libraries. We just have, we're going to, and we have a short announcement, so please be patient a little bit because we have some information for you. First of all,
well, we have to thank a lot of people for making this workshop possible. But in particular, we would like to thank Philippe and HP for having the idea some years ago of starting this series of workshops. And to thank Beatriz and Klaus who are here because they are the guilty ones for Losumar and I being in the field right now. So it's important for us that you both are here. Thank you. And our luck has been amazing yesterday, and without them, I think the things would not have been so smooth. Well, at least smooth enough. So Patricia, Malu, Gustavo, Natalia, Daniele, Vinicius, Hadi, Alexandre, all the people who have the yellow.
by the way, if you need anything, just look for the people with the yellow badges. Okay, so the short announcements. We have the certificates and the receipts for the people that pay the registration fee. We are going to make them available from tomorrow on. You will start on during the coffee break, so people don't leave the talks to get the certificate. We'll have somebody in the registration desk giving the certificates and the receipts. So from tomorrow on the coffee break and during the lunchtime, there'll be somebody there so you can get your certificates and your receipts. We have lunch here for people staying in the hotel. It's full board, so it's already paid. For people that are not staying at El Doutor, you can also have lunch and dinner here. The cost is it is 55 reais per meal. We are planning a sightseeing tour on Wednesday, but I'll have to tell you more about it later because I still don't have the itinerary. I mean, I contacted the agency, but I still don't have it fixed or the prices. But we are planning to have some sightseeing of the city on Wednesday afternoon because it's a free afternoon, right? I skipped something because we are live. Just so you know and don't say anything that you might regret afterwards. But please don't try to connect from here. This is for people, if you want to send a link to somebody that is outside here, is okay, but don't try to connect because our internet is already, it's not that great already. So if everybody tries to connect to this here, nobody will be able to do anything.
And just, this is all new for us, so as long as we understood, each section will change a little bit the link, so we'll try to find a way to be broadcast.
For today, I think the link is that one, but maybe for tomorrow the link will be another one. We don't know yet. We are learning to do this.
And a warning, if you start having problems with the internet, it's because of us.
contacted, sorry.
Yeah, so just be patient, and we are trying to sort out a little bit, to split a little bit the band so that we don't interfere with your connections.
We will try to have this on only during the talk, so probably during the coffee breaks, lunchtime, and happening, the internet will be a bit better.
This is all an excuse so that you don't use internet during the talks.
And because of that, I mean, the camera is right there, and it's showing on the live, but it's not perfect. Especially the screen is not perfect. So if the speakers can send us the PDF file of their presentations before their presentations, we are going to put it on the web page so people that are outside here can download the presentation and follow you with their own presentation, their computer, if they want to. If you you can send it by email, either to me or to Paula, and we'll put it on the web page. Okay, so Wednesday night is the conference dinner. It'll be a barbecue in the
area further here, close to the swimming pool.
Everybody is invited, either if you're staying or not in the hotel. So it's going to be 8 p.m., right?
Yeah.
8 p.m. Proceedings. We didn't say anything yet because we were not sure this is what's going to happen. Now we are almost sure. There will probably be proceedings for this conference, and it's going to probably be the same journal that the previous one were published. The AICS, is that right? HP. Is AICS? Okay. It's wrong over there. We contacted them, but we still don't have the final answer. So we will send you the information. Just be psychologically prepared to write proceedings. We are going to tell this probably every day, so you know. Now it's a bit early, you will forget, but on Friday there will be a shuttle that leaves about 2 p.m. to the airport. So it's a bus, actually, it's not a shuttle. So everybody is going to take the same bus to go to the airport. So be prepared to leave at 2 p.m. if you need to go on Friday. Finally, the coffee break. After the session, there's a coffee break. And the place for the coffee break is in the room in front of the registration desk. There's the registration desk. There's a room in front of it where the posters are. The coffee break will be there.
And your poster yet, and please, in this coffee break, just take a chance to go to the room and hang your poster there.
Anything else?
No, I think we are done.
We're done. Yes?
Concerning the lunch, it is paid directly to the waiter, or it has to be somehow registered when on the site to go to the lunch?
You don't have to register. I'm not sure how it works.
I think I have to double check, but I believe that you have to go to the reception and say that you want. Yes.
So can I decide just case by case?
Yes.
Absolutely. Yes.
The link to YouTube on the webpage?
Yes.
Because send the one that you gave to one of my colleagues, and it actually redirects to YouTube. Maybe I made a mistake while I was typing.
I'll put it on the webpage right now. Okay, so let's begin. So,
Our first chair, Beatriz.
First talk is by Cristina Chiappini, who's going to talk about discovering our galaxy with the large stellar surveys. It's 9:15, so we are going to be late by 15 minutes. We are going to finish at 10. Thank you. Oh, okay, we understand.
before, so. Ah, conector. Não, é aqui, ó, é pra mão, pra mão. É contato, ó. Não, mas é mesmo, a gente fez antes, certinho. É do seu carro. There's a connector without the pins. You have to put some scotch. I tested before it worked. Let me see. Aqui, ó. Assim fazer. Não mexe. Não mexe. Eu acho que não precisa, não precisa? Peraí, tem que colocar o bagulho que eu tirei daqui. Não sei. Okay, you hear me well? Okay, let's see if this works. This direction, no? Down. So thank you very much for the invitation. I'm very happy to be back in Brazil. I'm Brazilian. I left Brazil almost 20 years ago. So it's very nice to be back here. I was actually in this hotel 20 years ago, I think, in a conference of the Brazilian Society. I am an outside of your meetings usually. I feel as an outsider. I haven't been in the other two of this series. And I'm giving enough time to bring you. So I was thinking a lot about, I think it makes total sense to have this slot for galactic archaeology. That's how I named the field now, more than just chemical evolution. I'm going to show you something about galactic archaeology. The field became much more complex in the last years. And it's this complexity that I would like to show you. So you're not going to talk anymore about standard chemical evolution models or working with small samples of data like we used to do. Reddy also was in this game in the beginning of 2000. Now things got more complex, and we are going towards huge surveys with huge data sets, and there now the spectral libraries have a huge impact and a very important role. The talk is, let's say, it's a workshop here, so I will try to show you the complexity of the field, and then I'm going to show you something that came at hand that can change a lot the way we work, which is astroseismology. Astroseismology is something that brought to us the possibility to have the gravities of the spectral gravities extremely let's say, an order of magnitude more precise that any spectroscopy can give to you. And that has an impact on several things related to galactic ecology, but also to stellar lives. Okay. I'm organizing a youth symposium now in July in Potsdam. This makes a noise. Okay. I'm organizing a youth symposium in Potsdam, and the title of this symposium is Rediscovering Our Galaxy. And the reason is exactly that we have new data sets covering the whole galaxy, and we are really rediscovering the galaxy. We are leaving a local volume where we used to work, and we are now extending this to a much huge volume. That's very weird. Okay. These are the main topics that are hotly debated in the field right now. We are discussing how the halo of the galaxy was assembled. We need the use of cosmological models, and I will show you why. We are now getting a view of the bulge disk and the bulge halo connection areas. The bulge was something to reach. We had information only in the bad windows in high resolution, and now we are really extending the surveys to that region. We have surveys in the near infrared like Apogee that can cover all the region of the galaxy that used to be very obscure. We have fantastic photometric surveys also covering the inner regions. So all these surveys will be discussed. And what I'm going to show you in particular is that a lot of the discussion in the conference will be devoted also to disk. It's now understood that there is a lot of other process that matters, history and gas inflow in the disk, but things like secular evolution. The stars are born in one place of the disk and they are moving to another place and they lose memory of their kinematic. And so the only thing you can know, the only way you can notice a star is not from a volume where you're studying, is because the star has moved from another place and brought a chemistry pattern of this other place. On the other hand, if you look to the kinematic of the stars just look like a local star. So it's something that has to be considered, and it's a very huge impact in the way we work. Then also we are going to discuss in the meeting also the impact of astroseismology and the first release of the Gaia data. And we are preparing for the even larger surveys that are coming in the next years, which is WIV in the northern hemisphere and the foremost in the southern hemisphere, spectroscopic surveys. So all the work that we have been doing in this area is started in a very small volume, the Hipparcos volume here, picturing this illustration, right? So this is, do you have a pointer also here?
Yes, I'm the green button.
Okay, so this is the sum, and the Hipparcos volume was for where we have parallax and proper motions, and from there we could do a lot of studies of the orbits of the stars and combine this with chemistry. That's how the chemical kinematic study of the Milky Way started. We learn a lot in this volume, but what we need now, given the complexity that we are seeing that exists now, we need to move forward, leave this Hipparcos volume and see the galaxy as a whole. Some of the things that we see in the volume, we cannot explain without getting a view of the inner galaxy. Some stars from the inner galaxy end up in the Hipparcos volume, and to be able to constrain what's the efficiency of this kicking of stars from different places, you need to have a better understanding of the bulge bar area. So you need really to leave. This means that we need a global view of the galaxy, and we need the chemical and kinematic information, which means we're going to have to combine photometric and spectroscopic surveys, huge. And as I said, astroseismology comes at hand. It's something that I'm going to show you, it was discovered in 2009, comes at hand because it brings for you for free the gravity of magnitude more precision, and that will help all this game. So if we have this, if we need this overview, so the goal is then to be able to explore lower signal to noise ratio data, because if you want only to have very high signal to noise, your samples shrink in size, and also lower resolution data. You cannot now be sitting on very high resolution data to do the thermodynamical thing. You need high resolution samples combined with low resolution samples. And this will enable larger numbers of targets, a wide coverage of the galaxy, and a contiguous coverage. We have to move forward from pencil beam surveys to contiguous coverage of the galaxy. So that's the objective that we are going forward, and that's the framework I would like you to have when I discuss here. In this context, especially in the moderate low resolution spectra field, stellar libraries, of course, have a key role. Now, the common method is that you have a grid of most times synthetic spectra, and you search in this grid to find the best match to your observer spectra. And then is a method used a lot for low resolution, for the clusters. Now with Muse, you can do a lot of globular clusters and so on. But it's also used a lot in this surveys data that I'm going to show you. In particular, Apogee, which is a high resolution surveys, 20,000 resolution, and is in the H band. It's also working this way, their pipeline. One of the main issues, as I said, that stayed along the way is this large uncertainty in the gravities. Of course, temperature is also an issue. We are convinced that we need to go for this overview of the galaxy, and that's the only way to then infer something about the galaxy formation. And that is so much so that we have been writing these documents to convince the ESA and ESO to do the huge investments that are needed to get those done. And the Gaia is out there. This is the coverage that you expect to have with Gaia. You see the difference of volume that we are covering if we have Gaia, but Gaia is giving you the photometry and the positions, and you need to combine this with a spectra to get the chemical information that Gaia is not going to give you. Gaia is going to give you the chemical information only to very bright objects. So you need to move forward. For that, we have to think about the big spectroscopic surveys, and in some sense, from the 1 billion stars that Gaia will measure, you have to pick up the best 10, 50 million that can tell you the best story. And that picking up the best 50 million is not such an easy job. And foremost is a spectrograph that is being built and will be in the VISTA telescope, a 4-meter telescope, and you have many fibers, and you'll be able to get this huge sample for us. I was the project scientist for most from 2011 to 2013, both from the galactic and extragalactic side. Then now the project scientist is Sophia Feltzig, and I am now together with Elsa Starkenburg and Eva Minchek, we are the PIs of the low resolution Milky Way bulge and disk survey. I am a chemical evolution person, and I'm a PI of low resolution survey. That shows you how much I trust that we can get information from low resolution. Of course, the foremost also has a high resolution survey whose PIs is Thomas Bensby and Maria Bergman. And the two surveys will be very well connected so that we complement each other in the best way possible. What Foremost and Gaia can do, and also we in the north is also a spectroscopic survey, is that Gaia will give you the parallax and the proper motions for these 1 billion stars up to magnitude G20. And you get radial velocities, good radial velocity up to magnitude 15. Here you see the error in the radial velocities as a function of magnitude. These are the Gaia curves, and what Foremost is going to do for you is going to extend radial velocities below 2 kilometers per second in uncertainty down to magnitude 19. And we will complement the chemical abundances for the stars between 14, 16, probably even 18. That's the goal. What is Foremost? Very quickly here, the VISTA has a huge field of view, which helps for this goal of doing a lot of stars and covering a big size of the galaxy. 4 degrees squares. We have 2,400 fibers in total, from which 1,600 fibers are in resolution that are above 5,000. And we have 800 fibers that are resolution above 18,000. So this is our high resolution mode, our low moderated resolution mode. So the idea is, this is being already in conceptual design. What is important for me is that for the low resolution, this is the range we are covering, and we have some experience in working with RAVE. RAVE was also spectroscopic surveys, one of the first that had a resolution of 7,000, and we have some confidence by working with RAVE that we managed to extract individual abundances also from low and moderate spectrum. And so we have some brave people on board, and we see that even from the low resolution, we see a possibility to obtain carbon, probably nitrogen, also some heavy elements that have importance for chemical evolution and understanding, especially in the metal poor region. And so that's all things we are looking forward with the low resolution. So this is a spectral, we are making input catalogs, we are simulating what we can see. This is an typical input catalog of our low resolution survey. This is based on the Galaxia models of the galaxy, simulated down to the magnitude that we managed to observe. Plus we inputted the Gaia errors. So the Gaia parallax errors will depend on the position, because the Gaia has several observations for a number of observations in the different position of the galaxy varies. So your error in parallax varies along the sky. So we have convolved our mod catalogs with these errors, and we want to pick up the best 10, 15 million. So you want to get the best of Gaia. And so, and this we have to do, but there is the risk of biasing the sample. So the bias of the sample is always something that we are very worried that we have to learn how to treat. And it's that's where we spend most of the time. But essentially, we're talking about a survey covering 27 degrees squares of area in a contiguous manner with chemistry and kinematics. A person that likes to speak without, that's not working. Yes. Yeah. So I'm not going to enter the details, but we are planning different catalogs. A catalog, the first one is what we call extended solar neighbor, is where the Gaia can give the best data. It's where you can have probably estimate of ages. And we hope for ages, we hope for distance that are with errors below a couple %. And then we have two other catalogs that extend to, here you see the scale, here is just a couple of kiloparsecs, this is the sun, this is the whole disk, seeing face on, edge on, and this is the bulge. We also hope for a survey of the inner region of the galaxy that's huge. Such like you have 800 to 1 million stars towards the inner region bulge to cover this information. So far for most, let's go back in history. Before we get into this future, that means we are investing money, we invest a lot of resources, and we believe we can then extract the formation and assembly of our galaxy by having this data. This is true. So we started from the Hipparcos volume. One of the main important things that happened in this Hipparcos volume was that I'm going to show here the work by Furman. It's a very beautiful sample. Look, this is a volume completed sample 25 parsecs. Now we are extremely local. Okay, and many things that we learned from this sample is it's very special sample because it's a volume completed sample, it's a high resolution, it has a possibility to define ages, he was able to discard binary, so it's a beautiful work, but 25 parsecs. Okay, so what we see here, we see some stars with this magnesium over iron high, and they also are old. This is age. And you see another sequence separated from this one, which is younger objects, and that has this relation with magnesium over iron decreasing with metallicity, right? Metallicity doesn't go directly with time, but it's more or less. This plot, together with more work by other groups, has led to the idea that the thick disk of our galaxy was formed very fast, and the thin disk was formed slowly. This is solar vicinity, so the thin disk at this position. And as you move in the disk from inside out, the time scale of the thin disk formation changes. So when you are more outside, it's slower. When you are more inside, it's faster. So the more you go inside of the galaxy, the more similar becomes the thin disk and the thick disk in terms of chemistry, right? So that was an important work, and we have interpreted this as these two sequences, and that's my PhD work actually, and where we suggest the thick and thin disks are disconnected things. The chemistry is telling us that. Subsequent work, we did, what does it mean that the thick and thin disks are disconnected? That means that I can model the thin disk as at the solar vicinity with this kind of star formation history. Here the scale is 13 gigayears, while the thick disk, you see the star formation is more peak and is done into gigayears, you have formed the thick disk. That's what it means, transforming in star formation history. Have a chemical evolution model that you put this as an input to this star formation history, And what you get is these two curves. So now you take whatever abundance ratios you have. I'm back here in 2008, okay? This was the year 254. Now you take whatever abundance you have and the group of Bainsby and also Reddy, and they assign membership probabilities based on the velocity of the star. So not only to stay anymore in the 25 parsecs of Fuhrmann, 100 parts of Hipparcos, and in this volume, they assign probabilities of the star being thin disk and thick disk. This is a problem nowadays, but more or less, they get also thick, more biased samples to thick disk, more biased samples to thin disk. And when you plot this abundance ratio, so here data is showing in magenta, the thin disk is showing black, you see you have shifts between the two volumes. And now I take these two models of chemical evolution that I do with different star formation history. It's not a fit to the data. I just run these models and look with good stellar yields and a good chemical evolution model, what do I get out? And when I see my curves, I get a thick disk curve that's in blue and the red curve that's here. And you see that the red curve tends to align more to the black points, and the blue curve tends to align more with the magenta points. So the chemistry is telling me it looks like that in the local universe, the local volume, you can explain the thick and thin disk with different star formation, time scale of formation. Thick disk form very short and fast, and then a thin disk form slowly. That's what the data was telling us. We were happy in 2009. You had also other kind of data that are showing this discontinuity. For example, in this work by Navarro, the alpha plus Europium, so two things that are made by type 2 supernova and will be more evident in populations that are formed fast. And you see that the thick disk and the thin disk, so classified, they look different. There is a big problem how you classify that. Okay, so everything looks cool. You have also external galaxy redshift 2 that seems to show large disks in rotation corresponding to thick disk time. And then you have simulations by Bourneau at the time showing this interpretation that the buildup of central disks and bulge of massive galaxies happens already at redshift 2. And then you have the secular evolution of gas protodisks. So you can form very quickly in a style of 1 gigayears in the simulation a thick disk. And later you need the further gas accretion to form the thin disk. Everything looks cool. Also, from the point of view of the data that we had at that time, there was this plot from the data is from Alice and oh my goodness, forgot. Quillen and Garnett, yeah, Quillen and Garnett, and this group then model another simulation. And you see that the velocity dispersion of the stars, a function of age, as you go to older stars, you seem to have this jump. And as people say, the jumping velocity dispersion show you that you have an early phase of very turbulent thick disk formation. And this here, more flat, is a thin disk. So everybody's happy. The simulation of Chris Brooker explained that this phase here with high velocity dispersion stars, old stars, are related to this early phase of galaxy assembly in the cosmological scenario where you have pieces coming together and it's all very turbulent and so on. Everybody happy. But this is 2008, to the point that I didn't even publish that paper that I just showed you fitting so well with the chemistry. What happened? Well, at the same time comes the Geneva-Copenhagen survey, which was an extension of the Hipparcos volume, but with chemistry. And they start showing that the velocity dispersion was different. It was not like they had before, but it was increasing, steeply increasing, and there was not this little jump. That poses a huge problem, because you need to explain how the stars get in larger velocity dispersions as a function of time. This requires another mechanism that's not anymore molecular clouds heating of the stars, because that saturates. So that poses a problem. That was problem one. Problem two was the age-metallist relation extract from the Geneva-Copenhagen survey, even if there are all the uncertainties there is, it starts coming out something that there is no relation. It's flat, it's scattered, and so on. Also, myself in this conference, I was worried with this little bit here. You see that the red curve of my model stops here, but the thin disk, so-called, has these extra points that are beyond this curve. Is this important? Yes, because this red curve is the thin disk at the solar vicinity, and I need to reach a chemical evolution that gives me the abundance of the interstellar medium today. And interstellar medium today doesn't have those abundance. It's solar in oxygen. So who are those stars, right? So in there, I say, well, it looks like they are not from here, but they are in the local volume, okay? And there were discussion starts about radio migration. Also, very important was in the Geneva, Copenhagen, there was this work by Casagrande, where they tried to infer some ages with isochron age with lots of uncertainties, but they start seeing also something very puzzling. If you take the stars in the local volume of the Geneva, Copenhagen, and make a metallicity distribution, so the number of stars is a function of metallicity, in a world where everything is standard, the most metal rich should be the youngest, right? But it's not like this. The most metal rich are intermediate old, according to them. That poses a problem. That poses a problem. This tail here of the metallicity be above solar, which is also those stars that I just showed you that were difficult for me to understand, they cannot be from here. They are older, right? So that was an important point as well. Another very beautiful work was done here by Trevisan, where they also studied these stars here, very metal rich, exactly in this tail, and they managed to obtain, with very high resolution, they managed to obtain ages, and they also showed those ages are not the youngest. They are intermediate old. So when you put all this together, and together with also something that was going on in the dynamic works, we start going to the conference and people have this kind of statements. This is the end of galactic ecology, chemical evolution model is useless, all samples are contaminated. Everything is like you wanted to study the galaxy, but it's a scrambled egg. The eggs are scrambled. Okay, so you cannot use this to infer the star formation history anymore. Okay, so even more huge was this push by Shoni and Binney, where Binney says, all this is the age metallicity, so metallicity and age. We can understand this very, according to them, we can understand this very huge gap in age methylation because the stars are mixed from all the radia. So you have such a huge radio migration that everything is mixed. That's why you don't have age methylation anymore, right? And more, they suggest that the radio mix of cell population with high velocity dispersion, those that I showed you, they want to explain the increase of the high velocity dispersion as a mechanism continuous due to radio migration, and that's what they try. And stars start a huge debate because their models don't have bar, they don't have mergers, and the kicking of stars from one position to the other also depends on mergers and the bar relation with the spiral arms of the galaxy. So it starts a mess, I have to say. In a conference in Potsdam in September in 2010, it was Ivan Minchev who was just in Strasbourg working with dynamical models, and he was finding even a more strong way to mix stars. And he was saying, this is the age metallic relation is flat. I found a mechanism in the anybody simulation. So he put this transparency. Is this the end of galactic ecology? And the same conference, there was Ken Freeman trying to work on another age methylation showing that probably there were errors in age of the age methylation. And he was believing that the galactic ecology still would eat the radio migration problem. So we lived really a time where the data was not clear, there was no consensus about on dynamical models, and there was a need to test predictions with chemistry for plus age outside the Hipparcos volume. Did we move forward? I say yes. And is the galactic ecology dead? I say no. But. Okay, but we have a big but in the area. Radio migration really is there, is making a bit of a mess, and we have to quantify how much of a role this is playing into deleting the information we need to reconstruct the galaxy. And we better find a way out because we have already spent a lot of money, right? To do this. Things have evolved. We now, there are many dynamical arguments showing that the radio migration itself from pre-assembled disks cannot form thick disks, so that cannot be the whole story. With bar, we even have more radio migration. I was working on this with Feminger and postdoc Brunetti, even was working with Benoit Famé on this. We end up working together later on in a chemodynamical model to see the impact of how the radio migration is acting. We developed together this thermodynamical model. I'm not going to have a time to explain you how this works, but that was the first time we could make some predictions that could be tested by the big surveys of how the chemical evolution standard is shaped by hydromigration, by how much. Okay, how we did this, unfortunately, we have to skip. But this is one of the brain of our output of our model. So you take this metallicity distribution that I just showed you from Geneva, Copenhagen. Here we take in our model the particles. And so this model is an anybody particle simulation in the cosmological scenario that we paint the particles in the beginning with a chemical evolution of the disk that we know it works because we know some of our models work, we saw this. And then you let the anybody do the mixing for you because of the words, because of the bar, and then you extract how your particles look like. So a particle from radio 3 can finish here, right? So now we take all the stars that are in the solar vicinity, which here we call from 7 to 9 kiloparsecs from the galactic center. Here's the galactic center. We take all these particles, and we look where they were born, because in simulation we know where they were born. And then we see the distribution of the birth radius. And we see that the total, not all stars were born here. Most were born a bit inside from here, like the sun. The sun could be exactly from 6 to 5. But there's a distribution depending on the age. And this tail here is being made by stars that are old intermediate. You can't then, you need to point out why is this happening. That's great. And you can take this model. This is the underlying pure chemical evolution curves of each radii that I give. And the thermodynamical model mixes for you in a self-consistent way. And you get out an age-metallicity relation that has a scatter. And has this distribution in terms of age. Now you want to test this. One thing that you don't get, and that's the interesting thing, is the alpha bar versus R, you don't get the thick and thin disk. Why? Because here we did a simple model to show the people that think that the radial migration can make for you a thick disk and a thin disk in the chemical space, like Furman, and we showed this is not possible. And here, had this been possible, I would have seen this continuity here, but it's not shown. So it's a model that fits several things, but do not fit the discontinuity in the thick and thin disk. Okay, so I have, we also have a nice prediction for the abundance gradients. So, abundance gradients in the Milky Way, iron versus radius. And here, our predictions is the mono abundance gradients, they stay the same. But the amount of old stars and young stars depend on your sample. If you have a sample above if you have a sample that here is the same as there. But here in this other panel, I plot only the particles that are up to parsecs from the disk. So you are dominated by the youngest population, less dominated by the old. And when I go up, 1 to 3 kiloparsecs, you see the young populations dominate little, the old dominate a lot, and your gradient flattens. And this you can see from the surveys. You have surveys like Segway, Rave, making gradients as a function of height from the plane, and you see exactly this. And you can very well understand this with this kind of modeling, right? And you can do the same for the magnesium and the iron. This is the gradient today, but you see it's a mix of ages. That is a complexity. Your model has also to predict the abundance gradients variation with time. Okay? So our model fit. Okay, so now after we had this model in 2013, we will need to move forward to see how can we use best the surveys that we have already to test this kind of thing, and how can we plan the next surveys up to where we can go with the surveys we have now and what we still miss to go forward, right? Okay. Then you need the first thing you need is distance. You need distance for filled stars, and that's not easy. So there is Bayesian approach. Using the Bayesian approach to determine distance, there are codes that do this. Bidding was one of the first, but there are other groups, and we here, together with a collaboration in Brazil, the Brazilian participation group within Sloan, we have developed also spectral photometric distance code to give distance to the apogee stars especially, but also to the semi stars, any kind of survey. If you have Red Club catalog, as the case of the Red Club catalog from Bovi with apogee, you can reduce your uncertainties to 10%. If not, your uncertainties will be 20-30% in this volume of 3 kiloparsecs. If you want to go beyond that, then the uncertainties start growing. So with these other surveys, we expect from the Hipparcos to something like 3-4 kiloparsecs. Very nice, with all the surveys that are around there. listed there. This is the kind of survey. Here you have just showing you the rays and together with the segue, how complementary they were. Here in Z over X. Here the rave giants, here the segue dwarfs. And here the amazing extra information we got once Apogee got starting, because Apogee is in the H band and could fill the gap. You see, the other surveys cannot get in the obscure region of the galaxy, the Apogee filling the gap that we missed, where most of the disk stars are. And we started work on this. The first year of Apogee data, together with my master's student at that time, we start seeing the importance of using the seismic log G. This is where it comes. If you take the log G of the Apogee pipeline minus the log G that we have from Kepler and Pro at the time, I'm going to get to that, you see there is a relation. Separate this log G in order to get better distances, the riser distance, which are very dependent on the log G in the spectral photometric code, is going to be bad. And once we did this, we could do something that was leave the very local volume and look to the alpha Variro for some discontinuity in different region. You don't seem to have this part, two sequences, and in the inner region you have even more two sequences. Was a big improvement. Before you had this fantastic data here, but look, just few stars by Benzier collaborators, Alvis Britten collaborators, and they have shown that this upper alpha stars when you go outside the disk, and we could in the first year of Apogee already extend this to samples larger. First year of Apogee, but then later, already in the later years 12, this was the coverage of Apogee, and we in the paper of Hayden et al, we could do this alpha Variro of the Fuhrman plot difference in this radius and also at different heights from the plane, and in this way help to constrain the model. So really expand. You also that using this data, it looks clear that the thick disk of our galaxy, over position of populations, and the thickest part of the disk outside is made by younger stars than the inner disk. Okay, so we stayed with one little problem, which is not little, it's probably very important, that there is a discontinuity in the alpha Variro plane already in the Fuhrman plot. Why is this? And for explaining this, we need now ages. And the thing is that we have pushed forward the most we could, but ages is one important thing, is a discriminator, and everybody's going after ages. A miracle in nature. That's very nice. The seismology of red giants was born. Seismology, astroseismology was known in solar stars, in main sequence stars. But if you get this for giants, you can use these giants. Once you have the seismology, in short, I'm gonna tell you, when you have this, you can extract the mass and the radius of the star in an independent way. Once you have this, you have the distance and the age model. The age is model dependent. That means you can have an age and the distance of a star that's very far away if it's a giant. So there is a huge potential on this. So essentially, this all started in March 2009 with the publication of a letter in Nature entitled Non-Radio Oscillation Modes with Long Lifetimes in Giant Stars. Once you had this was 300 stars found in Corot. The Corot satellite was the first one to find this. And in the long run, so we had to look to this star for 150 days. What did we have? The first, we immediately got together to see how to use. This is the sun. These were two fields of Corot in the projection ZX. Here, seen from above. You see that one of the fields passes the inner parts of the galaxy, the others go to the outer part of the galaxy. Without spectroscopy, we could already use the seismic relations to determine distance for 2,000 stars. Beyond that volume that I just told you, of 3 kiloparsecs, we went beyond. And the errors, the uncertainties, were in the order of 3%. Okay, so there's a huge gain there. And that's what we show here. But it was also clear, and also we could then see that that there was a different mass distribution towards the two sides. And we could assign that this has to do with when you leave the plane, the stars get older. You could see this, because one field leaves the plane and the other field stays on the plane. But we need to go forward because we need the spectroscopy, because you need the spectroscopy information to add to the seismology so that you get the ages. Okay? Essentially, the seismology, you measure those parameters, and there is some relation that give you the mass and the radius, and you can get masses of the order of 10%, radius certainty of the order of 3%, and there are many people working on this to confirm if that's the case, using spectroscopic binaries and so on and so forth. Okay, there's a huge industry of how this works, and the very important point is that you can get log G. And once you get log G, the precision is 0.003, not 0.3. 0.003 dex. And that makes a whole difference in everything for many areas. So I have spoke 37 minutes. I continue here now on the actual seismology for another 10. Let's see. So why for giants this is so nice? Because for giants, the age versus the mass. Once you have the mass, you get age. And if you know the metallicity, it's even more precise. This is a track, and that's how it depends. And there was also the development of not only this what we call the scaling relation, but using really a Bayesian approach where you enter information on the seismo, on the spectra, on the photometry. You do the Bayesian approach, we decrease the errors, and you get a very nice idea of the age together with other parameters, including extinction in that region. Okay, so that's nice. Once I saw that, the Corot people were very much focusing on finding extrasolar planets. There was a little group looking to red giants, but they were like a bit outside. They invited me, this group, to give an invited review there to see what could be the importance of 2011, what could be the importance of this technique for galactic ecology. And I focused there in getting Corot to go to the bulge, to look to the bulge more, filled more to the bulge, because imagine if you have the age of stars in the bulge. That would be a huge impact, because we believe that if you have the bulge of MDS here is just, we know today that it's made of several MDS, but we think that here in this metal poor bulge stars are as old as the metal poor old halos. And we would like to see if I had the Corot checking there and seeing some images of the -1 stars, that would be a very important thing. So after this meeting, the Corot people were making an extension of the mission for 3 years. And they realized the importance of Corot in this, because at that time we had 2 astroseismology missions. One was the Kepler, but the Kepler field was fixed in one field. The Corot had always 2 fields in the disk. So to do the kind of galactic ecology we want to do, which was to get age as a function of radius, the Corot was fantastic. And so the Corot, while Kepler was on the heliocentric orbit, they observed always the same region of the sky. The Corot instead point in different directions, both in and out region of the galaxy. This means that it was possible to identify niches for each mission and to perform complementary projects as possible. So we wrote a proposal to the Corot, and they accepted it. And they pointed the Corot to the bulge. Okay? So we were very happy. We opened champagne in October, but then in November, it died. And so we didn't get the bulge though. Okay? But we were almost there. But we didn't get depressed. We were sure that it was was going to rescue us in this problem of galactic ecology. We knew that with good chemical evolution models, we could infer the star formation history, but then we would need to get a feeling of how much of this radial migration and so on was mixing, so we would need this good distance, and the way out was clearly now, after this turbulent times that stars migrate, the way out was to get eight good orbits. That's the way out. So things got more complex, more data, more precision age, more precision distance. Astroseismology was in the way out, but then the community of astroseismology is a different community. And they are very much, of course, there are uncertainties, there are precision, best accuracy, and so on and so on. So we entered into this game, and that was a complex thing for the moment, but we have already some outputs. So the impact of seismology. First impact, distance can have uncertainties of 1 to 2%, and we have papers showing this. and you can live beyond 3 kilometers. You can go beyond 3 kilometers. That's the first impact. Second impact, but you have only 2 fields, so you're not going to do much. You need more. What happened is that then once Corot died, Kepler also had a problem. And that was an amazing thing. Kepler had a problem. And look what happened. With Kepler problem, it became like Corot, more or less. Not really, because Kepler is long time. What happened is that the K2 mission was born. And the K2 mission was now doing several directions in the disk. Why? So what happened is that the Kepler-2 mission started in June 2014 after the failure of 2 reaction wheels that made the observation in the original field of Kepler impossible. And the new mission allowed for a stable point at a field around 80 days. Still, it's not 150 days, but 80 days. It was possible to get enough information, and that start a whole group of people also to learn how much information you extract and what's the accuracy you extract from 80 days instead of 150. But now Kepler was doing the whole disk, or not only, but several directions. So it was fantastic, right? But we had already started working. This is Friedrich Anders, my PhD student. He will need a postdoc soon. And Marika is a postdoc working with us. Friedrich then was working more on Corot, combined it with Apogee. And Marika was working more with Rave and Gaia ESO, combined with K2 and Corot. Okay, that's the way we divide our work. So just to show you a bit here, the Corot G, as we call the Corot plus Apogee, our Corot G. Here are the underlying work Apogee stars, the 2 Corot fields, and the Kepler field, precursor of K2. Before K2 was coming, we did this. As I said, this made the join of 2 big communities, and we had to understand each other. And so we had some meetings, and I organized a big meeting now here. We were 70 people. There's I edited a double issue of the AN, now in 2016, a very nice volume, where we collected all the problems and uncertainties and difficulties and what we gain when we combine spectroscopy and astroseismology, also in terms of spectral libraries and everything. So the Apogee, we are using massively Apogee. The Apogee stellar parameters, as I said, from a grid of synthetic spectra, where you search and get these parameters. The difficulty here is that you have in the H-band a lot of molecular features, and this requires a grid that goes beyond the usual effective temperature, gravity, and microturbulence, but you have also to have the carbon over iron, nitrogen over iron ideas on the top of over iron. Gonna need that. So the resulting is a 7D grid that comprises several million of individual spectra and all the complications that come out from there. More technical issues, I'm going to jump. And then you derive abundances from this for all these elements. Okay. Of course, this all can be improved. And one of the things, and then you calibrate your abundances, and your things have to be calibrated. And of course, one of the first issues that come is the log G. So the log G of Apogee for the stars that have Kepler abundance, now in this field, you compare and you get this. What do you see here? These are the dwarf stars, but Apogee mainly is concerned of giants. Apogee does not correct from rotation, so the pipeline would not work if the stars rotate too fast. For the giants, this is not the case, but for the dwarfs, that can happen and can mess up the way you extract. So you see this here. The log G, you see that there is a trend, right? And you also see something interesting. With the seismology, you can tell if a star is on the RGB or on the red cloud. That's very important. And you see that there seems to be a bit of a difference between the red cloud, the RGB and the red cloud difference between the pipeline. So they decided to calibrate it using the RGB, to use this calibration for the log G of the whole Apogee then. And this, you don't need, because this essentially is a red clump, so you can get the distance from red clump stars without needing the log G, in some sense, right? Okay, so this is all the calibration of Apogee in this paper of John Holtzman. This is the calibration they are using. But you use this to the distance and so on, but they do not recomplete the abundances once the log G has been changed. That's one thing. But still, the abundances are very nice. And then we started using some things also that once we had the Corroget sample, so apogee with those abundance plus the Corot information. The first thing was a letter where we found that some stars that are here, this is alpha Variron versus age now. Now with apogee we have age. We found that some stars were alpha enhanced but young. Alpha enhanced means old. We were told in the school, in the university, told no. We found alpha youngers that were younger than 1 giga-year. They are young, okay? So why? Well, this we're not the only ones that found this. Other groups that found this, let me just jump here. There are several explanations. Probably these are close binaries, probably these are stars where a matter caves over them, and then the mass is really giving an age. But there could be other more interesting explanations. There could be some fleeces of the galaxy where the galaxy stays like that without participating of the chemical evolution and suddenly form stars and the stars are kicked out. Could be. So there are interesting things. How do we know? Well, by having more data, right? And by having other people working on this as well. One thing I just want to show, with the Corroget, we publish now a catalog, everybody can use. There is the abundances, the ages, everything is on ADS. We have masses, radius, distance, extinction for 600 of these Corroget stars. Uncertainty in this is 2%, in radius 4%, in age 25%. It's the first time we see alpha Variron correlations with age in this range of galactocentric beings. And we do see in this paper migrators from the inner galaxy. First comparison with thermodynamical models with alpha Variron relations with age. So things are getting complex. Ages are not so easy. We have probability distribution functions in age. We still have probably working big beams of age, but we cannot color, for example, take the apogee data, the Corroget data in the outer part of the disk, and you see that you start having some weirdos. Those people should be young. They are too metal rich for this beam, and so on. You can start gaining a leverage of interpretation that is very huge. Very important, the last one I want to show you is that after 20 years of debate of how was the gradient varying with time in the galaxy, was it steepening with time, the abundance gradient, was it flattening with time, all people discussing this. With Corot and apogee, we can get the evolution of the abundance gradient as a function of time. This is another paper, it's a set, it's in press here, using the sample. Let me just skip this, I show you this. The prediction, this is the data, this is the Cepheids plus the young Corot data. They are on the top of each other, showing that the ages are good. And this is the first time we can see this abundance gradient, so always the iron versus radius. 1 giga-year between 1 and 2 older stars. And as you get older, you see a scattering increasing, but you also see some people that always stays here. These are migrators. They are high metallicity, and they are already here. This is a mock catalog. We take our simulation, which is this one. This is our simulation. This you see today, the younger stars do not migrate, but here, when you go to older stars, this will be the input of chemical evolution pure, and this is on the top of it the migration that kicks stars out, so those stars migrate. So you see this, you take a mock, so you observe this model as you observe Corot, and you get this. You kind of trying to understand what you're seeing. It's not bad. And you see that the gradient was the evolution of the gradient. You have now, this is the abundance gradient in the galaxy as a function of time. In the past, it was flatter and it steepened with time. And we compared with all different people that had tried to do this over the years, and to see how difficult it has been along the years and how Corot can help you that. And you can also have the abundance gradients of the magnesium of Variron vary with time, which is an amazing important constraint for the chemical dynamical models. And the last thing is just this. We go then a step further. That's the work done by Marica Valentini. We have two papers accepted right now. Essentially now we do the same. We take the Corroget, the Corot plus the Gaia-ESO. The difference is that we are not in the outer field. The Gaia-ESO complements a lot this from the inner field. So we have more inner stars than in the sample of Friedrich Anders. Here we have 498 stars for what we also determined distance, radius. This is still not out. We have to still finish the paper. But these cells are different. We now have used, different from the other works, we have used the seismic log G to recompute the abundances. And that gives you much more precise abundances. I'm not going to enter detail, but I have the numbers here if you want. And what is interesting is that in the inner field, we start seeing even more of the weirdos. These are the weirdos. Young alpha-rich stars are appearing even more in the Gaia-ESO field. So, and the final point is that we have used also now the K2 and RAVE. Finally, RAVE also has some stars in common with K2. So RAVE was the last survey that didn't have help from astroseismology yet. The data on this side of RAVE that just came out, we have been able to calibrate log G as well using the K2. This is the new catalog of RAVE that's published in Funder et al. It's very interesting if you see the effects of this calibration. And for 87 stars of RAVE, we did have the K2. So Marika did this extra abundance work, and we see from RAVE low resolution that we get exquisite abundances. And this is a way to check this. This is a way it's a different way to work with the spectra, where the spectra are projected in some dimensions, and you see some island here, for example, is a map, and you see that here is predicted that you have an island of metal poor giants, and we find two of the giants of RAVE to be metal poor there. Okay, so let me just finish here. The summary is that we understand better the thick disk. We have something that we can call the geometrically defined thick disk. We have also chemical thick disk. But we see that some more complex thermodynamics are happening in the inner part of the galaxy that could be related to the young alpha-rich stars. We're still not sure. We have more to do. We need more solid constraints. We need H's, and we need to leave this volume. We are going to do this with Tegas as well, with Gaia now. And we are looking forward to Apogee 2 and the K2 data and Gaia, combining with these big surveys. And so I get back to my original transparency of the talk. The complexity in interpretation of the kinematic data of the Milky Way suggests that we need this global view, and we need now to go to better exploitation of low signal to noise and low resolution data, large number of targets, wide coverage, and contiguous coverage. That means stellar libraries of high quality for which you can do this job in a much more precise way with the help of calibration samples that have astroseismology and benchmark stars, and so that's the way for the future. Thank you.
Questions, please? Yes.
It's very good talk.
Thank you.
Few years of life was, I thought, very beautiful. Now we made very complex.
Yes.
A lot of data. So, the thing is, you need to touch upon these galactic streams. Galactic streams.
Yeah.
There are plenty in the thin disk which are localized, and they probably come from galactic perturbation from the center.
From the center.
Yeah, galactic balls. And I think the Gaia is going to make them much more precise definition of these. I don't know, you call streams, we call galactic streams or superclusters. And people thought those are evaporated open clusters.
Yeah.
But they are spread over, they're not clusters.
Yes, spread over. So,
But
yes.
if you see thin disk distribution, and then you see spikes on the thin disk distribution.
Yeah.
Blobs.
Yeah. So people are trying to do this more like moving from chemical labeling, as we call, to chemical tagging. And the tagging is that the idea is that you could figure out these clusters of the stars that belong to this cluster a little bit from the chemical. And people are trying this. So there is some work now, we're using these projections, work of the spectrum. So for example, the Gala group has just published a paper where you have identified some groups of this. They even found a Pleiad stars, right, outside the group that they figure out it is. So it's possible that we're going to get to a time where we'll be so precise using other kind of tools that we're not used to use now, that you could individuate part of these streams and extract them a bit. But to do the whole chemical tagging of the whole galaxy, I am a bit afraid that, I don't know.
Maybe
I
these
don't
are
know.
the ones which are contributing to these contaminations.
Yeah.
Age contaminations, even abundance contaminations.
Could be, but it's abundance contamination. They are weird because they, you mean, yeah, there could be these streams that kept the gas old now with high alpha, and they are forming stars now.
I have a comment about it, about thick disk. This nice picture that you showed from the press release by Ron Mincher's paper with the gradient. So what we did over the past several years, we observed several galaxies which are edge-on, where you can probe thick disk by just making a long slit spectroscopy. Just offset the slit from the main axis. And nowhere we saw the age gradient. We had like 6 or 7 galaxies so far with very deep data. And in none of them we detected age gradients. So the question how the thick disk form is still far from being closed.
You talk about integrated spectra, right?
Yeah, I'm talking about integrated spectra, but if you have, if you look at this.
Yeah, I know, but if, for example, I didn't show here, but if there's a way to determine age for the field stars of apogee, like there's a paper by Mahimatik recently, and they have shown that there's a gradient in age by looking at the apogee data, although these ages are also uncertain, but they look like. So what this is a very important link we have to make with the extragalactic work, is how sensitive will be the integrated spectra to such a small difference in age that I'm in the right place to ask. I'm not sure if you guys are at the level of this way to tell the age, because even being inside for individual stars is already hard to pick up this age.
Yeah.
It's mixed.
I
don't think you would see much of a difference, because the difference is not like it's not between 100 million years and 4 gigayears. No, the difference is
it's very hard to tell the difference between 10 and 12 billion years. It's impossible, essentially, I would say. But it's much easier to tell the difference between 4 and 6. And we have galaxies with intermediate age thick disks, and we don't see the population gradient.
Yeah, I don't know. Yeah, this is a point that we have to check.
Thank you. I don't work in this field, but I'm fascinated by it. And I have to say straight away that I think your talk was a very comprehensive and convincing set of arguments, and so well done. But I have a few reservations.
Yeah.
And let me first go back to about 1970 something, when Bernard Padgett, at a meeting very similar to this one, between what he called the ultimate refiners and the broad sweepers. The broad sweepers were those who use ever such a lot of stars as quickly as they can at low resolution in order just to get the numbers, to get big statistics. Whereas the ultimate refiners were those who just did 1 or 2 stars extremely thoroughly. And then they could put together the kinds of, they could match, mix together the kinds of results that they found, because they were complementary rather than competitive.
Yeah.
So I would take issue immediately with the first of your points there, where you want to move forward, better exploitation of low signals of noise, etc. Because you are tending to lose something. With low signals of noise, you will not acquire, certainly the resolutions that you mentioned. You won't get the sorts of information that is crucial for determining ages, because you will lose binaries. You will lose that information about how many stars are in fact binaries, and therefore you make a false deduction about their ages.
Yeah.
And we now know that it's not just 25%, it's more like 50% of stars in the sky are in fact double in some way, and that is going to be quite a big knock to the basic relationship that you're based on.
Yeah.
And so that, I think, is
I'm very happy you brought this point. First of all, I was a very good friend of Bernard. I loved Bernard Padgett. And I used to think only really very much the way he taught. And I come from this perspective. I come from high resolution, the data abundance. I always prefer smaller data sets, but I can trust in. And I am a person that work now, I had to bridge this, I work in the 2. I have 1 foot in the very old way of work. I work with Beatrice in the board, very different abundance and so on, and I have another foot in the big surveys.
That must be very uncomfortable.
It is, but I'm used to this community, you see, and I can see how this step forward because I can see from the theoretical point of view how much is important the statistics. Some of the questions I can't keep the way it was, but some of the questions I can't anymore. So I see, although, that I need the people that are working on specific stars and have stars. Everything else is anchored on those. We call them for the canal, for example, we call them these gold samples, where for which you know the parameters better, and from there you're trying to extrapolate. As a PI of a low resolution, moderate resolution survey, I am fighting for my signal to noise. You can be sure, but there is a limit. There is a limit. This is a survey shared with many other sites. So we have to find ways to improve, but keeping, of course, this worrying. The binaries is you kick the most important point. We have also Klaus Forman showing this several times, how difficult it will be when we have to live with so many millions of targets and we can say 0 about binaries. That's an issue, it's an issue. And people are working on this, how can we circumvent this problem? But the galactic archaeology questions are so rich that you can answer part of them with different approaches. So this is not at all to take all the work on high resolution and individual work. It's a complementary work. I'm very aware of that.
And there's also the fact that if you work solely at the low resolution, you then miss the oddballs, which are the ones that actually people are fascinated.
Exactly. Exactly. Yeah. But in the high resolution, for example, in the Furman sample, exactly, it seems that we are missing a part of the thick disk that's more metal rich, which is not in this sample. It's too small sample, for example.
So I want to follow up on the comment of Igor about some indeed unresolved population analysis. So we had a work looking at the bulges of galaxies above the plane. So basically, it's a thick disk, but then it's the bulge above the plane, and that showed also in principle, old population. Although I agree that it's very hard to exclude that there's some young stars. What was special was that the MG over Rv was so high. So the magnesium over iron is higher than anywhere in giant ellipticals, and this is clearly a sign that this is an original, say, primary population. And this is, I think, also what we see in our galaxies. We take
Why is it very high? How much?
0.5, 0.6.
Oh, that's very
It's
high.
very high. It's now published, and more than just at all. So last month, and I find it very, very interesting because it basically shows, for example, that bars cannot be destroyed and reformed and so on.
Yeah, I have this feeling, yeah,
Yes.
so long ago, but yeah, there is data that shows that. Yeah. I'll check. Thank you very much.
Question here?
Thank you, Peter. Okay, so this is related to your comment and question also. Well, the binarity information and the multiplicity information will come from Gaia, from astrometry, from pure astrometry. So this you can take that into account. And the low resolution versus high resolution. Actually, what you need to do, I think, is to analyze the big surveys, so the low resolution surveys, but anchoring everything in the high resolution surveys. So actually, you need to analyze both at the same time.
That's what we're doing for most. We have the high resolution and low resolution. They will have the same spectral instrument, and that's the way to go. Hopefully, we're going to manage this. But also, in the apogee, you can see some obvious binaries. You can take it out because they have such a high precision in radio velocities that part that is fabricated. But I know that many we will not be able to take it out.
But very technical concerning the foremost. All the fibers, you said that there are about 2,500 fibers. All the fibers will be positioned on the preselected targets, or there will be some constraints by the construction of the fiber positioner. That simply you will take some of the data of the spectra randomly, just under the constraints of the technical technical placement. Because it is the case in Lamos. In Lamos, they basically can place some fibers, but the rest is automatically selected by the algorithms from the rest constraints of the fiber mechanism from catalog. Simply from catalog, they select the targets, but they are not targeted for the particular survey. I am asking if there is some possibility for some serendipitous discoveries that are behind these massive multispectral surveys.
Okay, that's a complicated question, but so there will be an algorithm to place those fibers. People will enter with their input catalogs. We will be so spoiled that we will have a Gaia input catalog by that time with a lot of extra information. But the foremost works with all science at the same time, made in parallel. So at the same time we're doing the galaxy, later we have to do the AGNs or we have to do the cosmology survey. So every catalog has to be inputted and there will be a complex algorithm that will optimize it the way that foremost will observe to the best. There will be extra fibers. So the consortium surveys, we use some amount of these fibers, I think it's about 70%. There will be an extra fibers for other projects that you have to see how we're going to add up into this algorithm. So I am the chair of the co-chair of the survey simulation and strategy simulations, and that's what we are looking, how to assign the fibers, how to be sure that we have observed the input catalogs at the best. So we have defined something that's called figure of merit per survey. Each survey API defines their figure of merit, very difficult job to do, but we manage. And we trace how this catalog is being observed along the 5 years altogether. Now, there certainly will be space for serendipitous discovery, because this is a huge catalog with, in the case of Gaia, really huge catalog. We give to the system twice as much as we need at least.
It's a hope for the future for the machine learning.
Guys, we have to go here. Thanks.
I have one.